Alright, hello. So in this video we talk about addition and subtraction of vectors. Right. So let's say we have two vectors, the conventional A and B. This be B and let this one be A. Now we know in order to add them vectorially, we must place them in such an order such that the head matches with the tail of the two vectors. That is to say that I'll take this vector here, A, and I will put it right there of the same length and the same direction. So this is my, well, rather clumsy looking A now. Let me get rid of this one. And then the vector that we get by joining the base of B to the head of A, that is this one right there, drawn in red or orange, well, that's a resultant, and we know the resultant is nothing but a fancier name to the vector sum of A and B. So there it is. Now, this is how we dealt with addition of vectors, so it's the first part. But as you can see in this video, we'll try to tackle down the other way to look at addition, or basically we'll tackle down what it means by subtraction of two vectors. So if I have two vectors, A and B, I want to ask myself what would be A minus B. Can I represent that? Will it be a vector or would it be something else? Well, let's try to tackle the more bigger question. The bigger question being, yes, it will be a vector. Well, that's the bigger answer. Anyway, this would be a vector. So this is something that the rules of vector addition and subtraction tell us, that if you perform any addition or subtraction on a vector, that still yields a vector. And not only that, if you have a vector A and then you transform it as, say, 3 times A, then that is still a vector. The only difference between these two vectors of A and some constant 3 multiplied by A is that if this were our A vector of a length of, say, 4 units and pointing in the northeast direction, again, you have your map in this manner, so this is east, this is north, south, and the remaining west. Then 3 times A is also another vector of the length 3 times of that of A. So this would be 3 times 4, and 3 times 4 is 12. So the length of this vector would be 12 units, but it will still point in the northeast direction. And the reason that happens, this is 3A, this is A, and the reason that happens is because 3 is a positive number. So if you multiply A or any vector by another positive number, then the direction of the vector doesn't change, just the magnitude changes. So say we had another vector like so, B, and we want to find a different vector which is 2.5 B. So we want to know, how does this vector look like? Well, if this is B in this direction, then 2.5b would be the vector in the same direction, just 2.5 times the length of this. So if this length is L, then this length would be 2.5 multiplied by L. So this would be 2.5b. And again, this number is positive. Since 2.5 is greater than 0, the direction does not change. Right, so with that clarified, we can now see what happens if we multiply a vector by a negative number. So let me change my color, and let me get rid of the question that we're wanting to answer. Right, so I can even get rid of this for the moment. Right, so if I have a vector, say, now let's take C for that matter, C. So this is a vector of length 2 units pointing in the northeast direction. Now I want to ask myself, well, what would be minus 2 times C? Right, so in order to answer that, we look at another vector in the same direction, because we are only multiplying the vector by a constant. There, that does not change the direction, no matter what you do. So the vector will still be pointing along this line. But because of the negative sign, it will be now pointing in the reverse direction. Now you would see that I've drawn my -2 c vector as a rather longer vector than my original c vector. And the reason that is because this length now would be 2 times the original length. So this would be 4 units in length, and this would be -2 c vector. So what would have happened if I were looking for -c vector? Well, if I have c vector pointing in this direction, well, -c vector would be another vector pointing in the same direction, the same northeast line, but in the reverse order. Now, the other striking property of this -c vector is that the length would still be the same, because we're multiplying the original length by -1, or basically by 1. And 2 times 1, or for that matter, anything times 1 is 2 itself, or the same number itself. Therefore, this length would still be 2 units. But the vector would now be pointing in the opposite direction. This would be -c vector. So, to state it in more general terms, now this is the way physicists and mathematicians prefer. If you have a vector v, and you're looking for a vector lambda times v, the lambda is a constant, is a scalar constant, then lambda times v would also point in the same direction, direction line rather, as v. But the magnitude of lambda v would be the magnitude of lambda v would be the length. And what we were talking about earlier was the fact that the length would be multiplied by the modulus of lambda. So in some aspects, the modulus function behaves as the mathematical modulus function. So you can see here that if I want to figure out the length of the new vector, lambda times v, well, all I need to do is know the length of my original vector. And I need to multiply it by the modulus of lambda. Now, if lambda were, say, 2, then 2v would be twice as long. And if lambda were -2, -2v would still be twice as long, because the modulus of -2 is still 2. So this is how it's stated in many books. Now, with that in mind, let us try to answer the question that we started this video with, which was, what happens if I take A and I subtract B from it? We convinced ourselves that looking at A and B is the same as looking at A added to another vector of -b. Now, if I call -b vector as a new vector of B prime, or B prime vector, then that will be the same as adding A to B prime vector. Now this brings us back to familiar territory. So let us draw A and B to start with, to look at what's happening graphically. Now A, say this were A, and this were B. So you have A vector here, pointing in this direction, and B in a rather horizontal orientation. Now, B prime is the negative of B. So that means if I take this length, of howsoever long this is, and I extend it in the reverse direction, then this would be -b vector. Therefore, A plus B prime, and this is the same as B prime vector. Therefore, A and B prime, when added, would be giving rise to the resultant of A and B prime. And we can find that by drawing a parallelogram around A and B prime, or negative of B. Then, using this point and this point there, if we draw them up, connect them, then this would be, well, A plus B prime. And since A plus B prime is the same as A minus B, then this length here represents the difference. Now, what represents the addition? Well, that's a question that we have answered in the previous videos. If this is A and this is B, then we must complete the parallelogram in this direction now and join this point with this to get the resultant of A plus B. So to draw them in a bit more clear way, well, this length here, this vector here is A minus B, and this vector here is A plus B. So if you have two vectors, A and B, I'm going to draw them now in this manner, A and B, then A plus B is given by the diagonal of the forward parallelogram, like so. This is A plus B. And the difference of A minus B is given by drawing out minus B vector in this direction and adding this with this. So we must draw a parallelogram in this direction, in the reverse direction now, to facilitate, oh, that's a very curvy line, to facilitate this diagonal, to draw this diagonal now, and this would be, well, A minus B. So there you have it, the resultant or the addition and the subtraction of two vectors. So I hope this video made sense, and I hope it helped you to understand what addition and subtraction of vectors means, and not only that, but also what happens to a vector, say A, when we multiply it by a constant of, say, lambda. So all the best.